Good afternoon, everyone. My name is Park. Today, I would like to talk about VarGrad, a low complexity gradient estimator for variational inference. This is the outline of my talk today. In part 1, I will introduce motivations and contributions of the paper. And then I will explain VarGrad estimator. And then I will present analytical result, which will be evaluated by experimental result. Finally, I conclude part 1 with a brief summary. In part 2, I will present the progress and plan of the project. As you know well, variational inference approximates the posterior distribution with a parameterized family of distribution as shown in the figure. Vi finds the parameters pi then minimize the KL divergence. Since KL divergence is intractable, Vi solve an equivalent problem then maximize the elbow. It can be solved by stochastic optimization algorithm, hence we need to estimate gradient of the elbow. In the previous work, many gradient estimator of the elbow have been proposed, such as score function gradient estimator, reparameterization estimator, and combinations of both. Other gradient estimators were proposed by considering performance versus computational complexity trade-off. In this work, we described an alternative derivation of VarGrad based on the log variation loss. We show that the control variate coefficient of VarGrad are close to the optimal coefficient. We also show that VarGrad offers a favorable variance versus computational trade-off compared to other state-of-the-art estimator. This slide shows the gradient of the KL divergence. Here, log marginal probability is represented as shown here, where elbow and KL divergence are shown here. The gradient of the KL divergence with respect to the variational parameter pi equals the minus gradient of the elbow. This slide shows the relationship between log variance loss and the gradient of the KL divergence. For a given distribution, the log variance loss is defined as shown here. Proposition 1 states that the gradient with respect to pi of the log variance loss equals the gradient of the KL divergence. It implies that we can estimate the gradient of the KL divergence by estimating the gradient of log variance loss. We represent estimator of the log variance loss as empirical variance of S Monte Carlo samples as shown here. Applying proposition 1 by differentiating through the log variance loss, we define VarGrad estimator as shown here. It is unbiased estimator of the gradient of the KL divergence. This slide shows the pseudocode for VarGrad estimator. In the pseudocode, stop gradient is a function in software package as shown here. From now on, I will explain the analytical result. This, with a control variate coefficient, the VarGrad estimator is represented as shown here, where R hat, G hat purpose of reinforce is scope function estimator, and A is chosen to minimize the variance of estimator. In terms of variation reduction, the coefficient of the optimal A is defined as shown here. Lemma 1 states that we can express the optimal variate coefficient as the expected value of A VarGrad plus a control variate correction term as shown here, where alpha A VarGrad is empirical average of log ratio and the component of the correction term is defined as shown here. It means that the control variate coefficient of VarGrad is close to the optimal one. From now on, I will explain the variance of VarGrad estimator. Proposition 2 states that the ratio between the control variate correction and the expected control variate coefficient of VarGrad can be upper bounded by as shown here. Corollary 1 indicates that when proposition 2 is satisfied and KL divergence is strictly increasing in D, the variance of VarGrad is always smaller than the variance of reinforced estimator. From now on, I will show the experiment result. This slide shows the control variate coefficient of the VarGrad. The figure shows the ratio between the control variate correction and the expected control variate coefficient of VarGrad in the logistic regression model. It is observed that the ratio is small and uniformly bounded over F. We can conclude that the VarGrad estimator stays close to the optimal control variate coefficient. This slide shows the variance of the VarGrad estimator. Figure shows the variance of different gradient estimator in the logical regression model. It is observed that the variance of VarGrad estimator is smaller than the variance of reinforced estimator. Finally, I'll conclude part 1 with a brief summary. In this paper, we proposed VarGrad estimator to approximate the gradient of the KL divergence. We established the connection between VarGrad and log variance loss. It is shown that VarGrad control variate coefficient are close to the optimal one. It is also shown that the VarGrad has lower variance than conventional estimator. This slide shows the progress and plan of the project. Until now, we choose and summarize 3 papers and submit the project proposal, and understood the VarGrad estimator and prepared the progress presentation. From now on, we will try to understand mathematical analysis in detail, regenerate the simulation code, and evaluate the performance. Finally, prepare the final presentation and report. This is the end of my presentation. Thank you.